Oh, let me stop these windows here with the recording in progress story. Okay, so today's lecture, I'm going to continue my discussion of complex networks by describing, first of all, a very simple but very, I think, beautiful model that incorporates this feature of network densification. And part of the reason for showing models of this character is just to give you a sense of that, there's still many simple generative models of networks that have not yet been fully explored. And so this is just one of this genre of models. So as I mentioned last time, I just got to figure out how to make this thing advanced. Oh, here we are. So there was like two flavors of complex networks. The so-called sparse networks, where the average degree does not change with the size of the network. That is, the ratio of the number of links to the number of nodes is a fixed number as n goes to infinity. And then there are dense networks where the average degree is actually increasing as the network increases. And I showed like these examples last time that have this feature. And so what I want to now do today is to present to you a very simple model that incorporates this notion of densification and look at some of its very basic properties. And so the first one, so the copying model is the following. And as I guess I started to mention last time, it's sort of motivated by Facebook, which was that when you join Facebook for the first time, you will start getting annoying messages from Facebook every couple of days saying, we see that you are friends with X and X is friends with Y. Why don't you become a friend of Y? And this happens all the time. And so when you do that, then you'll generate more messages from Facebook saying, well, now that you're friends with Y, maybe you want to become friends with Z, who's also a friend of Y. And so this is a natural mechanism for adding more links to the network faster than you add nodes to the network. And so that is the idea underlying the copying model. So here is a very simple model, simple network. It's only got 3 nodes. And I, as a new node, join the network and attach to the central node of the network. And then in the copying model, the idea is that I also look at the neighbors of the initial node and attach to each of them independently with a probability p. So what happens then is that with a probability p squared, I will create, when I join that circular node, I'll also join the 2 friends of that circular node with probability p squared. And so I'll make a complete graph of 4 nodes. But I can also just attach to one of them or the other of them, or attach to none of them, and each attachment happens independently with a probability p. And so here, the basic parameter that drives the network growth is this copying parameter p. And what we want to do now is try and understand what is the role of P in characterizing the structure of this network. And so just to give you a feeling for what happens, here I'm showing now very simple snapshots of a network of 1,000 nodes where P is the variable parameter in the model. So in the first slide, I'm imagining P equals 0. So I'm building up the network one at a time, attaching to a node randomly. So this is what is technically called the random recursive tree. You attach to any node of the existing network independently of anything else, and you end up with a tree-like network. And so here, I've arranged the nodes in a circular pattern, so some of the links look very long, but the crucial point here is that we have one connected network, but it's sparsely connected. Everybody's connected to only one other person in the network. And now we ask, as we increase the copying parameter, what happens to the structure of the network? And so, whoops, jumped ahead. So here at point 2, you start seeing like a little cluster. So can you see my cursor here?
Yes, we can see it.
Okay. Hang on. Oh, hang on a second. I've been told there's some feedback here, so I'm going to take my phone and move it away. Sure. Okay, I hope that's better. Anyway, so we see that there's a little cluster of nodes that are more tightly connected. Some people are more still sparsely connected. We increase P still further, and we get now like some local clustering going on. And when P is 0.6, now it really looks somewhat different in character because it seems like there's a very densely connected part of the network. And when we go all the way to, well, 0.8, now it's hard to see because the links are so dense that it sort of fills up the picture itself. And then P equals 1, we end up creating a complete graph. Every node is connected to everybody else. What I want to do now is try and understand basic properties of this network analytically. And as you're going to see, for the very simplest property, it turns out that it is very amenable to analytic treatment. But before I get to that, let me just sort of give you an overview of what happens. And so here is, roughly speaking, a phase diagram of this copying model. So here, my basic parameter is the copying parameter P. And you see that when P is very small, one ends up with tree-like networks with a few small loops in them. And as you increase P, the network gets more and more dense until you get all the way to P equals 1, it becomes a complete graph. And so a natural question to ask here is, as a function of this copying parameter P, what is the nature of the structure of the network? And the way that we're going to try and analyze this in the simplest way is just to look at the number of links as a function of the copying parameter. And so what we're going to see, so I'm going to derive this, but I'm just sort of previewing it in advance, is that there's a phase transition at P equals 1/2. For P less than 1/2, the number of links is linear in the number of nodes. Whereas for P larger than 1/2, the number of links is growing faster than linear in the number of nodes. And so this is the basic feature of densification. And as P goes to 1, the number of links scales as n squared, which is what happens on the complete graph. So there will be this natural transition from sparse networks to dense networks to the complete graph as P passes through 1/2 and approaches 1. All right, so let's study the behavior of the number of links, the average number of links as a function of the number of nodes in the network. And as you're going to see, it's actually quite simple to understand this behavior. And I hope that the machinery that I've been presenting in the past 2 weeks will make what I'm going to show you look very familiar to you. So we want to ask, how does the number of links change every time I add a new node to the network? And so let's write down a master equation or a rate equation for the change in the number of links when I add a new node. So L of n is a number of links when I have n nodes in the network. I add one more node to the network, and how many new links do I create? And so the difference is we can understand in the following way. So initially I have some network, that's the blue nodes of the network, and I attach to what the central circular node. So that happens for sure, but we know with the probability P, I'm going to attach to all the other nodes of the network. So let's imagine that our initial node that we're attaching to has degree K. So that means there's K additional possibilities for attaching to the network. And each one of those additional nodes I'm attaching to with probability P. So the change in the number of links in the network is going to be the number of new links which I create. And so there'll be one link I create from the attachment from the red node to the circular node.
Professor Redner, if I may interrupt, there's this feedback that is not going. I don't know why. It's like a buzzing noise in the background.
You know what? Let me do the following. Let me shut off my phone. See if that does anything. Does that make anything better?
Yeah, I think, yeah, it's better. Maybe that was the reason.
Okay, so I shut off my phone.
No, it's actually, that's still there.
It's still there.
Yeah.
Let me hang on a sec. Well, I have a technical person coming to help me out. Just 1 second.
Yeah, sure.
Yeah, I'm not sure where it's coming from today.
I have my on Zoom. I have my microphone all the way off.
Yeah, it's
Yeah.
not that. It's some electrical thing. But
Okay.
let's try
Okay.
further from
Okay.
the microphone receiver.
Okay. Okay. Any better?
Well,
It's, yeah, it actually comes and goes. So
Okay.
now it's gone. Yeah, but it will come back. Yeah.
Okay,
I don't know if it's related to proximity to the laptop. I don't know.
yeah,
If you-
I don't
Can
know.
you, can you try to come closer to the laptop? Maybe it's some
Yeah,
sort of
I'm
interference.
like, I'm touching, I'm
Yeah.
holding my laptop right now. Does that help or make it worse?
No, nothing. I don't know.
All
It's
right,
gone.
is it,
It's a wave function. You measure it, it collapses. So
so should I
it's
continue?
done. Yeah.
Okay. So anyways, so we want to ask what is the change in the number of links? And as I said, we add one link for sure. And then of the remaining k neighbors of the central node, each one of them is added with probability p. So that means that I'm adding 1 plus pk additional links. And so that says that the change in the average number of links is equal to 1, the new one that I surely add, plus p times k average, when I average over all possible nodes that I'm attaching to, and since I'm attaching to every node equally probably, so I should just average k over the network. And the average number, the average degree we know is 2L over N. And so we have that the change in the number of links is 1, which is this node I add for sure, the link I add for sure, plus this additional one from adding to all of my friends. And the crucial point about this correction term is that this correction term depends on P in a non-trivial way. If P is less than 1/2, then that correction term is less than 1. And so we can ignore it compared to the 1. On the other hand, if P is bigger than 1/2, then that correction term dominates over the 1, and it dominates the behavior of this difference equation. And so using that fact, we have the following behavior for the change in the behavior of the number of links as a function of n. And it's easy by taking writing a taking the limit as n goes to infinity and just writing the taking the first term in a Taylor series. You can write down the differential equation. L dot is 1 plus 2pl over n, and that differential equation is easily soluble, and it has these 3 different behaviors. It's linear in n for p less than 1/2. It goes as n to the 2p when p equals 1/2, and so it joins up to the behavior of p less than 1/2 in a smooth way. And typically, when you have this non-universal or this time-varying exponent here that joins up to this value n, it usually is there's usually a logarithmic correction right at the critical point. And then when you see that when p is equal to 1, we have n squared, which would correspond to the complete graph limit. So very simply, we have a non-trivial behavior that the number of links has this linear behavior for p less than 1/2, superlinear behavior for p larger than 1/2. And so sublinear corresponds to the sparse graph, and superlinear behavior corresponds to the dense graph. And just to give you a feeling for what this looks like, what I'm showing you now is the distribution in the number of links for a fixed size graph. And you see that when p is small, this distribution is very sharp and narrow. And in fact, it's a Gaussian distribution in this limit. One can work a little bit harder and compute the variance in the number of links and the full distribution in the number of links. One finds that it's Gaussian. But by the time you get to p is 0.9, there's a huge disparity in the distribution, on the width of the distribution of the links. And this is actually another very interesting lesson about some of these growing network models, which is that there is lack of self-averaging. In many many body systems, if you look at many different realizations, then you expect to see variations from realization to realization, which should be small. So if I think about, say, the Ising model, below the critical temperature, and I make a snapshot of the Ising model, and I take many snapshots, and from that I compute the magnetization and look at the distribution of magnetization, well, that should be something that is, there will be a well-defined average value, but the variance around the average value should be small. And in this particular case, we have large systems. We're preparing them in the same way. And in some sense, it very much depends on what happens very early on in the process. If the network is small and by some chance I happen to join up to every other node of the network, that sort of bias sort of propagates to the very end, and one ends up with a very broad distribution in the number of links in the network. So that's a very interesting lesson about this type of model. So now we can fill in a little bit more of the phase diagram. What I've shown now is that if I'm looking just at links, there is a phase transition from linear behavior to superlinear behavior. And given the fact that links in some sense are the most simple-minded structural property of a network, one can naturally ask, well, what about triangles or complete graphs of size 4 or complete simplices of any given size? And I'm not going to go into this because it's a little bit more technically challenging, but suffice it to say that there's actually a second phase transition for triangles. So for p less than 2/3, the number of triangles is linear in the number of links, which is linear in the number of nodes for p less than 1/2. But the natural way of characterizing this is triangles is linear in the number of links. And above 2/3, we have triangles scaling as this L to the 3p over 2. So when when p is equal to 1, we have triangles scaling like link to the power 3/2. And then one can look at complete graphs of size 4. And again, there's another phase transition at 3/4. And one can continue this process for small complete graphs of any given size. And there's a whole sequence of phase transitions at values, critical values, that if it's an n site complete graph, there'll be a phase transition at n minus 1 over n, where one makes a transition from complete graphs of size n being linear in the number of complete graphs of n minus 1 nodes to scaling in this way. And so finally, and so this is the general answer. And so we have this general feature that for p less than 1/2, the networks are sparse. For p larger than 1/2, the networks are dense, but they're dense in a very rich way because there's a whole sequence of phase transitions of complete graphs of all different sizes. And I think that this is an aspect about these sorts of models that isn't fully explored yet. And I think it's very pretty and very beautiful. And I just wanted to expose it because I think it's kind of a very nice characterization of complex networks. And this notion of densification is not as fully explored as it ought to be. So I think there's still some room for interesting research here. Yes. Okay. All right. Okay. So I guess that is all I wanted to say about statics of complex networks. And so what I want to finish this lecture series on is looking at the various sorts of dynamical processes on complex networks. So, it's all well and good to understand the structure of complex networks. And again, it's still a very rich and vibrant field. But on the other hand, now that we know that we live in a complex network world, it's natural to ask, well, what about dynamical processes on such networks? And certainly the most natural one to think about is information flow. We all, we watch TV, we look at the web, we get our information from, wherever we get it from. And so, various sorts of pieces of knowledge are disseminated through this complex network. And it's of interest to understand, like, how does information flow across such a network? How do we characterize this information flow? And so I want to spend the rest of today's lecture just talking about the simplest dynamical model that there does exist of dynamics, which is the so-called voter model. So the voter model, as I say, is a really beautiful and simple model for opinion dynamics. And the way that we can think about it, so let me phrase it for you people there in the classroom, which is that suppose I lock the doors of the classroom and say, we are not allowed to leave this room until we all agree on where we're going to eat dinner tonight. So we're all going to go out for a group dinner, but we've got to agree. And suppose there's only two choices, restaurant A and restaurant B. And the dynamics of this voter model is the following, which is that I want to go to restaurant A, and maybe Sarah wants to go to restaurant B. And so but the thing is that I don't have a lot of self-confidence. I don't know Beirut very well. I don't know it at all, in fact. So if I say, well, I think I like restaurant A, and I ask Sarah, which restaurant will you go to? And she says restaurant B. And I say, wow, that's a great idea, because I have no self-confidence. So let's say restaurant B. And so the rules of the game is that you pick a person at random in the classroom, and the person queries a random other person in the classroom and asks which restaurant you're going to. And whatever the other person answers, the first person who has no self-confidence, because we all have no self-confidence in this voter model, just adopts the state of the person that they've asked. So that's what the voter model is. And so a natural question you might ask is, will we ever leave the classroom? Will we eventually reach consensus on which restaurant we're going to go to? And the answer is yes, we will reach consensus. And then a natural question you might ask is, well, how long will it take us to reach consensus? And so these questions about whether you reach consensus or not, and how long it takes to reach consensus, these are the basic questions of the voter model. So let me describe some of the mathematical properties of the voter model now. And I should say that the voter model is actually a very interesting model in the sense that oftentimes physicists come up with a model and then the mathematicians make it more rigorous. And in this particular instance, the mathematicians actually formulated the model, and then the physicists have run away with it because of its many applications to social phenomena. So the original papers were published, almost 50 years ago. And so let me describe like the absolute simplest version of the voter model. So let's imagine that for the sake of simplicity, that the voters are fixed to be on the sides of a regular square lattice. And let me, represent the voters as not, restaurant A or restaurant B, but think of them as like spin up or spin down. So we start our process by assigning for each side of the lattice a binary voter variable, either spin up or spin down. So here spin down is blue, spin up is red. So, and now the first step in the model is that you pick a random voter. So I pick myself, I'm a random voter. And what I do is that I look at the state of a random neighbor. So in this particular case, so I look at one of my neighbors and I assume the state of the randomly selected neighbor. So the point here is that everybody has zero self-confidence and just adopts the state of one of its neighbors. So for this example, 3/4 of the time, I'm pointing up, and I have 3 neighbors also pointing up. So if I pick a random neighbor, 3/4 of the time, I'll pick a neighbor who I agree with. And if I agree with my neighbor, then there's nothing to worry about because we agree. And so there's no change in my opinion. On the other hand, 1/4 of the time, I pick the person who disagrees with me. And so I change my state. And so that is the basic dynamics of the model. And so I repeat these steps of picking a person at random, picking a random neighbor, and I repeat the step over and over again. And as I'm going to argue, consensus necessarily occurs in a finite system. And why does consensus necessarily occur? Well, the thing is that we have here a stochastic process in which the fraction of up spins and down spins is changing with time. And as long as there's some disagreement in the network, then there'll be some dynamics. But if there is consensus, then there's no mechanism to leave consensus, because once everybody agrees with everybody else, there's no chance for a person to spontaneously change opinion here because it's only based on this nearest neighbor interaction. So once I've reached consensus, that is what's called an absorbing state of the stochastic dynamics. And that means that you necessarily must reach consensus because there's a finite probability of reaching consensus, because if there's a state where there's one person who disagrees with everybody else, eventually that person will be extinguished by the dynamics. And once it happens, then you're done. So we necessarily reach consensus in a finite system. Yes. Hang on a second.
It may be, I think it's coming from the left.
Okay. Oh, so I should stay away from the laptop?
I'm just wondering if maybe, if you're not going to use the whiteboard.
Yeah.
If we just.
Yeah, there was a very good spot in which you were standing that the
Here?
noise disappeared. Yes.
Right here.
Yeah, a bit further. Yeah, it's very funny. A bit to the right.
Even further?
To the right. I mean, okay, we're seeing it then in reverse. So yes, to the left. Yeah, I think it disappeared.
And it also gets worse when you move, so.
I see, okay. All right, I mean, the problem is that, so what, should we turn off the whiteboard? What should we do?
Right, so we could switch, are you gonna be using the whiteboard?
No,
or
I
more
don't,
likely
no,
just-
I'm not using the whiteboard.
What we can do is get rid of that microphone and just use.
Okay,
your computer.
okay,
And I think that's-
all right. So hang on a second, let's take a 2-minute break for like
Okay, sure.
technical assistance.
Okay.
Please.
Basically, the model is based on like name. Can you hear me now? Is
Yeah.
clear? Is my okay? So the model is based on a specific like specify first choosing an element and then deciding on which neighbor
Yes.
or like deciding which neighbor is going to affect this element. But my
Yes.
question is like, how do you decide which neighbor is going to affect this element if you have more than one neighbor? And especially if you have like two neighbors, which with like two opposites states.
Right. Right. So again, the rule of the game is that you pick a person at random and you pick a neighbor uniformly at random. So that is the rule of the voter model itself. So if you have more than one
okay.
neighbor.
Okay. Yeah, right. Yeah, I missed the second part. Yes.
Okay. Alrighty. Okay. So anyways, so let's continue on. And so the basic thing that I want to present now is how long that it takes to reach consensus on the complete graph. Thing is that what I showed you in the previous slide is I was thinking about the voter model on a square lattice. And as you know, it turns out that to solve for the consensus time on the square lattice is a little bit technical and involved. And so I want to present to you the simplest version of the model, which is on the complete graph. And so what I mean by complete graph is just as you see in the classroom, I can see all of you, you can see all of me. And so in some sense, we're all connected to each other because we're going to try and decide which restaurant to go to after the class. We can just pick anybody in the classroom equally likely. So the complete graph is just exactly that I think of that all of you in the room, you're all equally likely to ask anybody else in the room. And so we want to ask, how long does it take to reach consensus? And hopefully when you see what I'm going to show here, it's going to look very familiar to you because it's basically nothing more than a kind of a random walk process. So let me define T of rho as the average time to reach consensus when I start with a fraction row of people who are either in the plus state or pointing up or say they prefer restaurant A. And I want to ask, how long is it going to take us if we have such an initial state prepared? How long is it going to take us to reach consensus? And so once again, you know, the tools of stochastic processes allow us to calculate this in a very simple way. And so let me write down what the equation is. And I'll spend a fair amount of time explaining it because there's a lot packed into here. So the point is that I have a consensus time as a function of rho. And after a single event, when I ask Sarah which restaurant to go to, and I change my opinion. So what's happened is that after the opinion change has occurred, now I can calculate the time from a new state. So, you know, here, suppose that I wanted to go to restaurant B, and let's call that spin down, and let's call restaurant A spin up. So if I change my opinion from down to up, that means that the fraction of people who want restaurant A is now increased by an amount rho plus D rho. And the point here is that there is a renewal process going on in the sense that the time to reach consensus from rho, well, after I make a single step, so, you know, like more literally, I make a step in one direction. And then I have the same process, but starting with a new initial state from rho plus d rho. And so if I call R of rho, the probability of like hopping to the right in this, or, you know, where rho is increasing by 1, then the point here is that the time to reach consensus starting from a state rho is the time to reach consensus starting from a state rho plus d rho times the probability of making the hop to the right. And then there's a time dt when I made my step to the right. So that took a certain amount of time for me to make the step. So I think that let's try and sort of make this a little bit more concrete. So let's just look at the one term with the R of rho. So the probability R, I hop to the right, and I'm going to compute what that probability R is in just a moment. And so if here's my state space, this is the density of people who prefer restaurant A. And so a certain probability, I might be convinced to go from restaurant B to restaurant A, which means I hop over here because now the fraction of people preferring restaurant A has been increased by 1. And then at this point, it's the same process all over again. The process renews itself. There's no memory in the process. And so I have the probability, the time to reach consensus starting from rho plus d rho. And the probability of hopping to the right is just the probability that I have two people, I pick two people who happen to disagree, and the person who is pointing down changed to up. So I have to compute this probability that that this event occurs, that two people disagree and the downspin turns up. And so the point here is that the probability, if rho is a density of people that are pointing up, then the probability that two people disagree is nothing more than rho times 1 minus rho. And according to the rules of the voter model, once I pick someone who disagrees with me, I will always adopt their state. So the rate at which I change is 1. And so the coefficient in front of this factor rho times 1 minus rho is 1. Similarly, I could have been someone who preferred restaurant A and talked to someone who preferred restaurant B. And so I go one step down in this state space. And again, the probability of hopping to the left here, this left hopping probability is still the same. We need two people to disagree, but then the person who's pointing up will go to pointing down, but this happens with the same probability as capital R. And so these are the two possibilities for which the state of the system will change as a function of time. On the other hand, there's one more process, which is that I could pick someone who agrees with me, in which case we do nothing. And if we do nothing, then in the state space, we just start at density rho and we stay at the same point. And because these probabilities have to add up to 1, the probability of doing nothing, or like of picking someone who agrees with me, is nothing more than 1 minus L times minus R. And so this T of rho, this is what's called the backward Kolmogorov equation for the average consensus time. So there's a probability of hopping to the right times the consensus time starting from one step to the right, probability of hopping to the left times the consensus time from hopping to the left, and then 1 minus R minus L, consensus time where I didn't do anything. And for each one of these possible steps, I wasted a time, or I spent a time dt in actually making the actual move. And so the time itself is incremented by dt, the amount of time I spent in making this individual opinion change, plus the time that it takes from starting from the new point, because the process renews itself every single time I make an opinion change. So this is the basic equation that describes the evolution of the time. And the thing about this equation, which is really kind of useful, is that in principle, we're studying a time-dependent quantity. We're asking something about dynamics. How long does it take to reach consensus? But we write basically a time-independent equation for this consensus. And this is one of the most powerful aspects about this backward Kolmogorov approach, is that we are actually able to compute time-dependent quantities in terms of a time-independent set of equations. Okay. So anyway, so here was our equation, and all we're doing now is we're going to do a Taylor series expansion of this thing. And so this is straightforward algebra. So just Taylor expand, again, R and L were equal to rho times 1 minus rho, and 1 minus R minus L is a simple algebraic expression. So if you take this equation and do a power series expansion or Taylor series expansion in small d rho, and do it to second order, one finds a very simple equation for the consensus time, where here the derivative, the prime means a derivative with respect to rho. And so this is our basic equation. And this also has to be supplemented with a boundary condition, because if we're at consensus, then it means that the time is 0. So this equation has to be, because it's a second order equation, it has to be supplemented by 2 boundary conditions. And the 2 boundary conditions are t at rho equals 0 and t at rho equals 1 also equals 0. So I should also mention here that what we're focusing on is basically the unconditional exit time, which is that we're not caring, do we go to restaurant A or restaurant B? We're just trying to find out how long it takes for us to reach consensus. Who cares what restaurant we go to, as long as one of the two. And it's possible, though, if we really wanted to be a little bit more careful about this, we could actually compute the time to reach A consensus or B consensus. But for purposes of this discussion, I just want to focus on the probability of actually reaching any consensus at all. So anyways, this is the equation we have to solve. And it's a simple exercise to integrate this equation. And what one gets out of all of this is that the consensus time scales. The crucial point here is that it scales linearly with the number of people in the system. So, and by the way, I should also mention, I realize that this is sort of like a little bit implicit, is that an important feature here is, what is the meaning of this dt? What is the time taken for one single step? And you typically, one can define this dt any way that you want. So you could say it takes me 2 seconds to have a discussion with one of you to decide which restaurant we go to. But in terms of a physically relevant time increment, a natural time increment is that dt should be 1 over n. So that means that in one time unit, each pair of people has had a chance, or each person has had a chance to update their opinion. So this result that the characteristic time depends linearly on n is based on assuming that the dt here is of order 1 over n. So in a one time unit, everybody will change their opinion. And that's sort of the natural time unit that one should do, both in terms of a physical process and in terms of doing like simulations of this process. Okay, so so let me come to
Sir, I just have a question going back
Sure.
to the previous slide.
Yes.
Has this DT been explored in the regimes where it's actually density dependent rather than just 1 over n?
well,
So
I guess what I would say is that if dt was density dependent, then that would mean that when I go to this, when I take the continuous limit, there would be additional powers of rho sitting here. And well, okay, let me think for a second. Well, I guess I would say the answer to your question is no, I don't think it's been explored, but I guess the crucial point here is that one should define a characteristic time for a microscopic event that makes physical sense. And certainly from my perspective, having a dt that's proportional to 1 over n is like the physically relevant case. But maybe there's situations where dt should not be just proportional to 1 over the size of the system. If there's some sort of something else cooperative going on, which is that somehow if maybe the room is more crowded and people are more frenzied and maybe they're going to be more anxious or whatever, and so that could be an interesting feature. Okay. Other question?
oh, thank you.
All right. So what I want to do now is that what we've seen is that in this very simple version of a graph, namely the complete graph, the characteristic time to reach consensus scales linearly with n. And so this corresponds to kind of a mean field-like behavior. But it turns out that on complex networks, the behavior, the consensus time as a function of n has very different dependencies depending on the nature of the degree distribution of the network itself. And so let me present to you just, so here I'm not going to derive anything because there was a lot of derivation, a lot of mathematics goes into this that would not fit into like half of a lecture that I have available to me now. But let me just tell you what the results are, because the results are interesting and profound, and maybe they teach us something. So it turns out that the crucial point here is I'm looking at specifically at power law, or networks with power law degree distributions, scale-free networks, in which the degree distribution exponent is nu. And so if nu is bigger or equal to 3, then we end up with the so-called mean field-like behavior. So, for example, the complete graph, everybody has exactly the same degree. They have degree n-1. If I have a network of n nodes, and n times n-1 over 2 links. Everybody's connected to everybody else in the system, so everybody has n-1 other connections. And so in this particular case, when the exponent is larger than 3 and complete graph, it's just a delta function, one has mean field-like behavior in which the consensus time scales linearly with n. But what's really kind of remarkable is that if you increase the width of the degree distribution, the width of the degree distribution by decreasing the exponent, one gets that when nu is equal between 2 and 3, and this in some sense is the case that's most amenable, or the most interesting from the point of view of statistical physics, because it is a broad degree distribution such that the mean degree is still finite. In this case, one has this non-universal behavior with an exponent which is the number here, the exponent itself is less than 1. So this means you end up with fast consensus. And what's happening in this particular case is that you can have some nodes that have very high degree. And once somebody has very high degree, this node can somehow control the opinion dynamics of the entire network. So in some sense, if everybody in this classroom was listening to CNN news all the time and was getting, influenced by CNN news, so one node which has a particular opinion can really quickly disseminate it through the rest of the network. And so one gets faster, a faster consensus time, which means that the consensus time grows sublinearly in the size of the network. And if you go to the case of nu equals 2, this is kind of
Excuse me, Professor.
yes.
If you go back to the case where nu is between 2 and 3, if you look at the exponent,
Yes.
and then the numerator.
I see. There's a typo. I'm sorry. There's a typo there. Yes. You know what? I think that might be 2 nu minus 1 bracket divided by nu minus 1. So thank you for noticing that. Let me fix it. I'll look it up in the break because I don't remember off the top of my head, but I'll fix it. But thank you for noticing that typo.
Thank you.
Okay, thank you. Anyways, the point here is that for when the degree distribution exponent gets so broad, at nu equals 2, that degree distribution exponent is broad enough that the mean degree in the network actually diverges with n. So really a very densifying network. And in that case, the consensus time scales not as a power law in n, but just logarithmically with n. And in this very extreme case of nu less than 2, which would correspond in some sense to like a star graph. If I had a graph in which there's one node that's connected to everybody else in the network and nobody else is connected to everybody anywhere else. In this case, the time to reach consensus doesn't scale with the size of the network anymore. It just is of order 1. So this is the behavior of the consensus time as a function of in terms of this degree distribution exponent. This tells us the size dependence of the consensus time. And so this is, I've not presented you any derivation here. I've only kind of given you a sense of what's going on, but I hope that you get the sense that, first of all, dynamics on complex networks is a rich area. And for the voter model, which is the simplest dynamical process there's a lot of interesting dynamical behaviors associated with this dynamics. So I think this is a reasonable place to stop. So let's take a 5-minute break. I won't, and then we'll, I'll start again in 5 minutes. Very good. Okay, so anyways, that is the right answer. Very embarrassing. Anyway, so you see that the point though is that the time to reach consensus is getting faster and faster the broader the degree distribution is. So this is kind of an interesting feature because as we think we live in a more networked world where there's some people who are not that well networked and some people who are very well networked, like news sources, that actually is an effect that decreases the time to reach consensus. In this whole area though of social dynamics, I mean, the voter model is a very beautiful and very simple model. It's also a very dangerous model because it is so simple, it's very easy to be seduced by its simplicity and study just the voter model itself. But real social dynamics has many other features going into it. And so there's been a huge effort over the past 20 years in the statistical physics community to incorporate other more realistic features of voter model, more realistic features on top of the voter model to understand the dynamics of consensus or polarization. And certainly the issue of polarization is a serious one in the modern, at least in the United States. And it seems like, that there's some aspect of intractability that we don't really understand very well at all. By the way, it says here my screen sharing is paused. Is it, do you see the full screen?
Yeah.
Okay.
We're still on the slides with a different behavior, right?
Yeah, just this whole, yes,
Yeah.
exactly. Okay. So I'm going to just spend a couple of minutes just giving you a sense of like what went into understanding this behavior, because so far I've just presented this to you like black magic. So let me talk about oh, I see now it's not switching on my, that's strange. It's not switching, you're still on the same slide, is that correct? It hasn't. Yeah, because on mine, I'm going.
Yes.
Okay, let me stop the screen share for just a moment and start it again because it's, look. Screen sharing is paused. Let me stop share. Let me try again. Fortunately, I mean, it's too bad we're having some technical problems. At least it's at the very end. Okay. Very strange. It looks to me like it's dock to top. I don't get it. Resume share. Oh, I see. Resume share. I don't get it. It looks like I'm going to have to do switching the slides just manually one at a time, but I only have a few slides left, so it's not a big deal. Anyway, so let me give you a sense of like how I derived that result. And the thing is that so the thing is that we have a network that has degree heterogeneity. And so what we need to do is understand what is the role of degree heterogeneity in the dynamics of the network. And so the point is that there are nodes of different degrees. And so here, let me call rho sub k. This will be the density of up spins on nodes of degree k. And the simplest version of a network that has degree heterogeneity is something called the complete bipartite graph. So, by the way, can you guys see me here? Is there, or do I have to stop share altogether? Because maybe I'll do one thing on the whiteboard.
Yes, we can.
You can see this?
Yes, yes.
All right. So, this is.
No, we can't follow your handwriting.
Yeah, so it's in the pinned tiny mode. Yeah, now we see the whiteboard.
So let me go back to here. Yeah, so there's a very special type of graph. I mean, so we've seen what the complete graph is. So a complete graph of n nodes would be, I take n nodes, say here, example 4, and I attach everybody to everybody else. So node 1 is attached to nodes 2, 3, 4. Node 2 is attached to 1 and 3 and 4. And finally, this guy's attached. And so you have 6 links in a network of 4 nodes. And in general, there'll be n minus 1 over 2 links in a network of n nodes. So this is a complete graph. Let me now look at what I call the complete bipartite graph. So in the complete bipartite graph, we imagine that the graph consists of 2 types of nodes, black nodes and red nodes. And the way that you create the complete bipartite graph is every black node is connected to all red nodes and not vice versa, but not to black nodes themselves. So this guy's connected to this one, this one, this one, and that one. And for the case that I want to consider, let's suppose that there's more red nodes than blue nodes. And so now this black node is connected to these guys. And so this would be the complete bipartite graph. To give it a formal definition, let me call this K of 2, 4, because it's consisted of a group of 2 nodes and 4 nodes. And you see that the 2 nodes, these guys all have degree 4. Where these nodes all have degree 2. And so this, in some sense, is the simplest graph that you can invent that has degree heterogeneity. And because it's a complete graph, all of the techniques that worked on the good old normal complete graph to understand the voter model work for this complete bipartite graph. And so this is the way that we were able to understand the behavior of the consensus time on complex networks. So one point I just want to make here is that when you're trying to develop theoretical modeling, like looking at the absolute simplest case is really quite valuable. And so once we have this picture that we can think of degree heterogeneity in terms of the complete bipartite graph, so we could then define the complete bipartite graph, which has, nodes of degree, K1, K2, K3, to anything we want. We can actually create a complete bipartite graph with arbitrary degree distribution, and using the techniques from the complete graph, we're able to actually solve this network. So now coming back to the slides, if I can do this. And I don't understand. And so now it looks like the sharing is working. Oh no, it's stopped. Anyway, because
we can see the slide.
No, I know we can see it, but it's like when I advance it, I can't advance it. That's my problem. Very strange. So let me stop the share and just let me go to the next slide, because it's probably so share. I don't understand what happened here, but fortunately it's like in the last few minutes altogether. So the point is that the generalization of the complete bipartite graph to arbitrary degree distribution is something called the configuration model. So in the configuration model, what one does is one starts with a collection of nodes. Each one has a prescribed degree. And then all you do is just connect up all the links associated with so each node in some sense has like stubs, which are the degrees. So I have a node of degree, say 5. So it'll be 5 outgoing links from that node, and those are called stubs. And then all you do is you connect the stubs randomly, and this gives you a very mean field-like picture of a complex network. And so what I'm showing here is the behavior of the way that the consensus occurs on such a sort of heterogeneous network. So what I'm plotting here is on one axis is the fraction of spins up on nodes of degree 11, and the fraction of spins pointing up in nodes of degree 6. And the point here is that if I start in a state where I have a whole series of degrees such that the mean degree of the network is 8. And what I do is I say every node that has degree larger than 8, I call them plus, and every node that is degree smaller than 8, I give it the initial state minus. And then what I'm plotting is, so nodes of degree less than 8. So for example, 6, that's a density 1. Nodes of degree larger than 8 are 0. And so what one sees here is the time and development of the behavior of the system. So I start with nodes of degree 6, they're all pointing up, nodes of degree 11, they're all pointing down. And very quickly, in a time scale of order 1, they go to this diagonal line where the number of spins, where like nodes of degree 6 and nodes of degree 11, they have the same average opinion. And then on this horizontal, on this 45-degree line, we just basically have diffusive motion until everybody reaches consensus, either both 0 or both 1. And this happens for all nodes of any kind, any degree whatsoever. So this is the way in which the route to consensus occurs on this complex network. So once again, I am unable to advance my slides.
Maybe try the space bar. Maybe it will work.
No, I mean, I see it advancing on my side, but they're not advancing on your side. So I guess what I have to do is to stop the share. So this is going to be a smidgen tedious, but let me just, because I only have 3 more slides to go. So I mean, we can do this tediously right now. So, so the last topic I want to present is yeah, so I want to, so this is kind of in the realm of like things which are not known very well yet. So I want to talk about, I want to return now to generative models of complex networks. And I spent some time last lecture talking about the redirection model, in which if I want to build a network in a very simple way. And one simple way is that I pick a node at random, I ask who is its ancestor, and I attach to that ancestor with the probability R. So this was the redirection process that I presented last time. But now suppose that the network does not have any direct, like the links have no directionality with them. So here, when I picked a node, I picked my initial node, that was this guy over here. And then its ancestor is a well-defined node. There's only one ancestor. And so when I do the redirection, I necessarily go to the green node. And then we see that the probability of attaching to the green node by redirection is equal to the number of upstream neighbors that it has, these light blue nodes. And now let's go over here to the next slide. But now let's suppose that there's no arrows. So now when I select the same node as before, and then I'm going to redirect my attachment, then it's these red nodes that I can possibly attach to. So it's a different set of nodes than these blue nodes. So the crucial point here is that, first of all, this is an incredibly simple model. I pick a node at random, I say, who is one of your friends? And I attach to one of his friends. And let me look at the very special case where the initial node that I select, I never attach to him or her, I attach only to one of the friends of the initial node. So let's call this like certain redirection. So as you see, it's a very simple generative model. Anyone can write a simple computer program to make this thing run. And so you might ask, well, what is the structure of this network? And what is amazing about this network is this. So this very simple generative model generates very bizarre networks that are not very well understood. And so these are 3 examples of, and any example that I can come up with will have the same kind of behavior. And so the network has now been color coded according to the degree of the node. So the green nodes are what I would call leaves. These are nodes of degree 1. So you see that the network is sort of very modular in its character. There's this module over here where there's this huge central core. So the red node has degree larger than 1,000. So there's more than 1,000 leaves attached to this red node. And then there's a few links to the rest of the network. And you see there's another huge hub over here with lots of leaves. And then there's sort of smaller hubs and then other weird nodes that are sort of connected with degrees between 2 and 20. That's the green and the light blue colors. And so you generate with this very simple model, which can be described in basically, one sentence. One generates incredibly complicated networks. And let me just go to my next slide here. And so what I'm showing here now is for this certain redirection model, I'm plotting on a double logarithmic scale as a function of the size of the network, the number of nodes of any given degree. So number of nodes of degree 2, 4, 8, all the way up to 128. And you see that the data is really beautiful and very straight line. And so it clearly indicates that there is power law behavior of the number of nodes of degree larger than 1. And in fact, here what I'm plotting is what I call the core of the network, which is the number of nodes of degree 2, 3, anything larger than 1. If I add these things all up, and here I divide it by 10 to the 4, so it fits on the same line, this core of the network, all nodes that are not leaves, is growing in a power law fashion. And the crucial point, this amazing point, is that the exponent of this is less than 1. In fact, it's 0.565, plus or minus 0.001. And if you want a rational fraction that is close to it, it's close to 17 over 30. So I just present this because it's, to my mind, a challenge that we still don't understand, which is with this very simple generative model that we've generated a network in which almost all of the network consists of leaves, and the rest of the network consists of a vanishing fraction that's only n to the 17/30ths. And so one of the challenges in this particular model is how to calculate this exponent. If this is one of the things that I'd really dearly like to be able to do before I die, is to figure out what this exponent is. Okay, so again, because this was meant to be 6 lectures, and it was a little bit hard to try and figure out how to apportion my time. So I'm at my very last slide. So here's my last slide, which should have come up very naturally in the talk itself. So I'm done with my presentation. It looks like you can't even see what I have here. That's strange. That's my last slide. Thanks for listening. So I'm done.
Thank you.
Thank you, Professor.
Yeah.
They can unmute the microphone. Because they're doing it.
Thank you, Professor.
Sure.
Thank you.
Yeah. So I'm available for questions if you have any.
Yeah, could I squeeze in one last question?
As many as you want.
What are some real world or physical examples of networks like with the copying model, like the photo model? We said that it's very interesting to physicists because it has real world applications. What are some of the problems that behave this way?
Well, I would say that the most natural one corresponds to what happens in citation networks. When you write a paper, you might cite some papers. And certainly, I think what's very natural to do now is that if you cite a paper, then you look at the paper that you're citing and you look at the reference list of that paper and say, well, I cite, I'm writing a paper about the Ising model. And so maybe I look at a paper, like last year that did something on the Ising model. And I look at the reference list, well, maybe I missed something. And then I see that in the reference list of this paper, there's the citation to the original paper by Ising. So maybe I should cite Ising's original paper. So this notion of copying references down the chain as a function of time is a natural mechanism for this copying model. And then the other one, of course, is Facebook. I mean, that is a very natural one. And if you look at the structure of Facebook networks, they do look dense. I mean, it used to be that Facebook would give you their data. They don't give it to you anymore. But, you know, we did get data from them, you know, like maybe 10 years ago. And so based on that data, we were actually able to come up with trying to characterize the structure of the Facebook network. And the copying model is certainly something that describes it better than just straight attachment and no more further attachments.
Okay, thank you.
Sure. So I'm happy to answer any more questions as you have them.
Yeah, how about the description of the last construction of the networks, the non-directed redirection
Yes.
with no ancestors. So any physical problem you can think of that motivated the construction?
Well, no, I mean, what really motivated that construction was Facebook. Exactly that, because the point here, well, okay. I mean, Facebook is more like the copying model, but so why the redirection? You know, I guess the only point is that I guess it's more of the beauty of the model more than anything else. I mean, we found that in the case where there were arrows on the links, that the redirection algorithm was incredibly powerful. It allowed us to first of all, make the largest simulations that you could make on complex networks. That's also very useful for understanding some details. And also it provides like the solution for linear preferential attachment and cousins of linear preferential attachment, which is like shifted linear preferential attachment. So I would say it was a natural question that arose after we sort of understood the case of with the arrows, what happened with redirection. I don't know, I was talking with my collaborator, Paul Krapivsky, what happens if there's no arrows? And this led us to this incredible, beautiful model. So no physical example, but just a natural progression logically of trying to understand complex networks.
And maybe another follow-up question from last session when you talked about the variation to Barabas's construction, where you had that non-universal exponent. We were just having a discussion about that mu that appears in the exponent k to the
Right.
So how, I mean, it's definitely in the way it's looking non-universal, but do we have any measures on how big that is? So probably that different, because it's somehow related to the rates, right, of additions.
So we're talking about
Yeah, when you have things go linearly and then you have it appear in the gamma function and then
yeah, hang on a second. So let me just try and get to the right. So
I think it's here. Yeah, it's on this slide.
okay.
Do we have any measures of how big that mu is? So I mean, we could.
Well, no, the point is, this exponent nu here.
We lost the screen sharing again.
Oh, wow, weird. Let's see, where am I? Screen share. Sorry. Let's try. Here. Make it larger. Okay, so this slide, is this the one you're referring to?
Yeah, exactly.
And so in this slide, the value of nu can be any number which is larger than 2. So this mechanism gives rise to sparse networks because the fact that the exponent is larger than 2 means that the mean degree is finite and the mean square degree is also finite. So these are sparse. I'm sorry, I said that incorrectly. Nu larger than 2 means the mean degree is finite, which means that the network is sparse. So you know this number mu here. You know, again, I mentioned that it was this amplitude of the total rate, but that amplitude can be adjusted any way you want because you know, in the case where it was like a sub k was k to the power gamma, you know, then mu was like 1 and 2. But if you say that a sub k is constant plus k to some power gamma, because you have an additional constant, you can adjust the value of mu to be any number you want, basically. As long as mu is bigger than 1, that's the only constraint. Is mu will be bigger than 1.
Okay. Any more questions from the crowd? No questions?
Okay.
Okay, I think yeah, it's my turn now to thank you for the beautiful lectures and for really introducing our community to the out of equilibrium processes and leading all the way to complex network. And I think there's a lot of appreciation to the material given, and I really assure you that they're in the process of absorption and
Okay,
deep thought. And we hope, I don't know if you would also consider sometime visiting us in Beirut. You've kind of made a big fan group here that you have followers already.
Okay.
In a sort of copying model, because I know you and they know me, and now the recommender system is suggesting that they should copy me. So
yeah, well, who knows what the future will bring?
Yeah.
Let us for more tranquil times.
yeah, hopefully, but anyhow, we're very thankful for, I mean, the setting and for the team who's been helping you with all the technical stuff. We don't see them, but we're very much also thankful for their contribution. We're picking up very early in the morning to make this happen, so we're thankful for them.
Okay, all right. So who knows when I'll see you guys again, but anyways, thank you for listening and
Thank you so much.
wish you all the best.
Thank you.
Okay, all right. So long.
Thank you.
Okay.